Okay, so good morning. The last lectures, anyway, we were been looking at determinant and the properties of determinant. And the last lecture, I think, was talking about determinant and the row operations. So basically, the idea was to see how we can reduce a matrix that has non-zero entries so that when we are looking for the determinant, we choose a row or column that has the most number of zeros. So by introducing the zeros, all right? Anyway, that's what we looked at. And then one of the things, if you look at the course outline that I uploaded for you in Odell here, before determinant was actually what we're calling inversion of matrices. And so inversion of matrices just talks about what? Inverting a matrix or finding the inverse of a matrix. So this book. I hope you guys have been reading this book. So I just highlight the important theorems and things that I want you to guys to look at. I mean, ideally, this I think an easy book to digest. Now, I hope my birds here don't make noise, so I don't know how to alleviate this one moment. I show you. Okay, this should do the trick. All right, so this will help, I hope. Right, so yeah, like I was saying, just put as much volume as possible. Anyway, so I'm just going through the notes really. I mean, if I need to write something here, I'll write, but this book you have, so let's just go through it very quickly. I have a meeting in the next not too many minutes, but okay, fine, no worries. So the inverse of a square matrix A, this is n by n matrices whose entries are real numbers, generalizes the notion of reciprocal of a non-zero number. In other words, when we talk about inverse, it's just divide. The inverse of 1 is 1. The inverse of 2 is 1 over 2. The inverse of 3 is 1 over 3, and so on like that, all right? So matrix A is called invertible if you can find our matrix C. So when you multiply the two matrices from the right or from the left, you get the identity. Now the identity behaves like the one for matrices. The identity for 1 by 1 is 1. The identity for 2 by 2 is the main diagonals are ones and the other entries are zeros, all right? And so on like that. So, and well, okay. I mean, you can go through the other details. So A is invertible, and we denote its inverse by this. And so A times A inverse is A inverse times A equals identity. So given A and C below, show that A is in, well, so here now if you're given two matrices, like here you just asked to find, to show that these two guys are inverses of each other, you just multiply the matrices. The usual multiplication, I mean, I think that's pretty straightforward. I'm not going to look at that, surely. You know how to multiply matrices. You just multiply A times C. So this way, this is how you multiply matrices. In case you've forgotten, some of you may have forgotten. So I just remind you. So this is how you do it. For the first matrix, you go that way. And for the second matrix, you go that way. All right. So you just take 1 times minus 14 plus minus 3 times minus 5. It gives you 15. And so 15 minus that 1 is 1. And then 0 times 2. So that's 1. Then 1 times minus 3 is minus 3 plus 3 is 0. So that's 0. And then 1 times minus 6 is minus 6 plus 6 is 0. So that's how you get the first row here. Second row is this guy. You go that way again. So minus 1 times minus 14 is 14. Plus minus 10 is 4. Plus minus 4 is 0. So that's 0. And then this guy with the middle column is minus 1 times minus 3 is 3. Plus minus 2 is 1. And this is 0. So that's 1. And lastly, this guy is minus 1 times minus 6 is 6. Plus minus 4 is 2. Minus 2 is 0. Okay. And that's it. You can see we have already obtained that. So you continue and you'll find that. These guys give you the identity, all right? And anyway, fine. Now for applying for systems of linear equations, I will not bother looking at it. Now let me just delete this so that I can make my life nice, as I always try to do. Right, so we move down for exactly what I want. Yeah, so this is the first important theorem. 10.6 that says that let A and B be invertible matrices. Then the matrix A inverse, the inverse of A basically, is invertible if A itself has an inverse. Obviously, this is its own inverse. So the inverse, this is now you can read this as the inverse of A is A. So you're taking the inverse of the inverse of a matrix to get the matrix. And then the matrix A times B is invertible if B inverse times A inverse is, well, its inverse is this basically, all right? So what we're saying is the inverse of AB is B inverse A inverse, all right? And how you go about that is just to take, so proof of this, or the last one, the matrix, the A transpose is invertible and its inverse is the transpose of the inverse of A. So how would you prove that? Well, the proof for this would just be, oh, I'm having issues here. Yeah, so proving this, you see, when you say something is an inverse of something else, it means that when you multiply the two guys, you get the identity. So you're saying this, the inverse of AB is this guy. So that means if you multiply AB times this guy, you should get the identity. And sure enough, that's a proof. AB times what we're calling the inverse, this is what you get. Here now I can help you in terms of the multiplication again. So AB times B inverse, you have this, and then now you open the brackets. Now matrices are associative. Associative means that it doesn't matter the order you pick them. All you have to do is you pick 2 by 2. I mean, 2, and then 2, and like that. Like you're multiplying numbers. So you're multiplying numbers, you pick 2. If you have 6 numbers you're multiplying, you just have to do 2 by 2 by 2, pairs as you go on. 2 times 6 times 3. You pick 2 times 6 first, and then whatever you get, multiply by 3, and so on. So in this case, you multiply B times B inverse. That gives you the identity, which is that. And then the identity times any matrix is any matrix. So this just reduces to, the identity we say is like 1. So this reduces to A inverse times A inverse, which is the identity. What does that tell you? That these two guys are inverses of each other. The inverse of AB, which we denote by this, is that one. Likewise, the inverse of A transpose is the transpose of A inverse. So how do you check that? We just take A transpose times what we're calling its inverse. So here now something that I think appears in the, in these notes up there, but when you're talking about transpose of matrices, so here what happens is that one step here that I didn't tell you is that so you're talking about A transpose times the inverse of transpose of A. So you can pull out the transpose for the two matrices. So I actually have told you it's here. They change the order. In other words, if I have A times B, I think there's somewhere where it says that upstairs. Anyway, transpose, this equals B transpose times A transpose. And so this is what you're applying here. So A transpose times the transpose of A inverse, you pull out or you factorize the transpose, they change the order, it becomes A inverse A. And then now A inverse times A is the identity, and the transpose of the identity matrix is the identity. So that just tells you that actually it turns out that the inverse of A transpose, which we are denoted by this, equals the transpose of A inverse. Okay? And now a nice exercise for you I would give you is I give you like some 2 by 2 matrices and ask you to verify this one or this one. That would be some nice exercise. All right? Right. Then now, having said that, let's continue to scroll down. Computing the inverse of a matrix. Now, how do you get the inverse of a matrix? You can do it in 2 ways. Now, before you go, remember we've been talking about determinant. So this is assuming that we don't know determinant. So I can tell you now. What's the determinant of the identity matrix? The determinant of the identity is always 1. I'll get to those properties later as we go on. But yeah, that's what it is. And the determinant of diagonal matrix, I think we looked at this, is you multiply the diagonal entities. Okay, it may be upper triangular, or lower triangular, or both, in which case it's diagonal. Anyway, so far, how do you compute the determinant of a matrix, the inverse of a matrix? To get the inverse of a matrix, actually, you can apply the row operations. So basically, I just summarize, I just say, let me just remove this. Okay. So basically what you have is, well, all this you can read. I just summarize for you, then you can check. It turns out that you just have to apply the row operations to this matrix. So you have your matrix, you can call it like the augmented form of a matrix. So you have a matrix A that you want to find its inverse, all right? You want to invert it. So when you write it this way, then you have a matrix, so a bigger matrix. You write the matrix and then you add or append the identity on it next to it, okay? And then you apply the row operations to this matrix to reduce this part to the identity. Whatever will come out on this side is actually the inverse of A. And that's only possible because there's some matrices you can invert. If it's possible to find the identity on this side. This is using the row operations, okay? The three row operations, we are calling them, interchange of rows, add a multiple of a row to another multiple of a row, or multiplying a row by a non-zero scalar. Those three, all right? And that's what the whole of this describes, which I don't want to look at because I think you have the book and you can read, okay? And you are good at this. So, for example, now here they give you an example of a question here. I just go through this briefly. And the question is asking you, I think I can, yeah. So find the inverse of A, given that A is this 1, 3, minus 1, minus 2, if it exists. So solution, you are expressed it in augmented form. So you have A, the identity. When you write I2, we mean identity 2 by 2 by 2, 2 by 2 identity. So you have your matrix A, and then now you append the 2 by 2 matrix there. And then now apply the row operations. Now here we can do it very quickly together. So basically what happens here, I can get this guy upstairs. All right, you stay up there. So what you have is, so you need to make this side the identity, if possible. So one thing you can see already here, if row 2 becomes the sum of row 2 and row 1, it's just row 1 plus row 2. If you fix row 1 is 1, 3, 1, 0. It stays as it is. Then row 2 is row 2 plus row 1. So 1 plus minus 1 is 0. And then 3 plus minus 2 is 1. Then 1 plus 0, 1. 0 plus 1, 1. So row 2 becomes this. Row 2 is row 1 plus row 2. Okay? Then we're here. We make this one a 0. Which one now? Well, okay, I don't know what they did here, but we want to make this one. Let me see whether I can highlight this. Good thing is, yeah. So we want to make this guy a 0. How can we do that? Well, we can multiply this guy by minus 3 and add a 2. Or we can just say we multiply by 3 and subtract. All right? We just multiply this guy by 3 and subtract. So I don't know what you want. But since I'm using their notes here, they multiply by minus 3 row 2 plus row 1. That gives you the new row 1. So you see, then you fix, row 2 is fixed. So it's 0, 1, 1, 1. That is fixed. And then here you have 1 plus minus 3. Minus 3 times 0. So it's just 1. And then 3 minus 3 is 0. And then 1 plus minus 3 is minus 2. And 0 plus minus 3 is minus 3. So this is the new matrix you have. And now guess what, ladies and gentlemen? This one here is the identity. We have exchanged. So now we have this. We start with this and we end up with the identity here. So now what we have obtained, this guy is the inverse of the matrix. Nice. I suppose you already knew that, some of you, I think from previous classes, but fine, no worries. Okay, next. You can be asked to find a inverse of a bigger matrix. At this time, since I'm running for a meeting, I will not bother. You can go through it, and I think if you get stuck, you just ask me, okay? Now, previously, I mean, in linear algebra 1, you learned what a vector space was. And maps between vector spaces, we're calling them linear transformations, all right? And a linear map or a linear transformation, which we're using T to represent them. So I'm going to revisit that again. So here I am, ladies and gentlemen. Let me just delete this. We'll remove this from our screen. Okay. So we revisit that. what do we have? So invertible linear mappings. So one of the things we said, we can say again, it still occurs, is that matrices actually, the way they arise are just representations of linear transformations. That means that any matrix you have actually describes some kind of linear transformation. What do I mean by this? That a matrix that you have anywhere in the universe is a map between a vector space to another vector space, all right? So like now here we say let T, a map from the vector space of Cartesian product of R copies Rn, n copies of R to another n copies of R, be a matrix. And then the star matrix, the representation of this map is a matrix A, and suppose that A is invertible, then the inverse of this map exists. All right, and this matrix will be A inverse. Okay, that's basically what we do. And yeah, I mean, I don't know whether you want me to go through it then. The star matrix is like that. So when you do a composition, now here we talk about composition of two maps. We'll have a map which will be the identity. All right. So this is saying that we TA sends Rn to Rn, and then TA inverse or T A inverse takes Rn back to where it came from. And so that gives you the identity. All right. Now, so here there's a very important theorem that I wanted to look at and discuss with you guys. So let me see whether I managed to talk about it, and then probably this will be the central object of our study this morning. Let me just sip my coffee here. So, so let A be an n by n matrix, a square matrix, okay, with entries real numbers. This is what it's saying, eh? The following statements are equivalent, all right? This is a theorem that is cyclic. Cyclic means that A implies B, B implies A, C implies D, D implies E implies F, G implies F, H implies I, and I implies A. So you go back. So when you have any of these, you have all the others. That's basically what this theorem says. And this is quite powerful. This is quite important, okay? So let's just go through it and say what? That, so, I mean, if A is invertible, then A is rho equivalent to IN. Now, this is just saying, remember the thing we've just discussed here, that if A is invertible, what this means is that, now allow me to write over here. A invertible means A inverse exists, all right? And this is just translating, saying that if you start with this, you can always reduce this thing using the row operations to this, the identity, and then you have A inverse. So a matrix A is invertible if this is true. I mean, so this is an even only if situation, all right? So A invertible, this is what it means. So it means A is rho equivalent to IN. So rho equivalent is basically saying that we have this kind of thing. In a sense, it's like the reduced row echelon form of A is the identity. That's what we mean by rho equivalent. That is the reduced row echelon form of A is IN. So this part is the original matrix somehow, but reduced or transformed, okay? And then if you apply this to a system of linear equations, x is a variable, equals 0, this will only have one solution, which is the variables are 0. Oh, now someone is calling. One moment, just one moment. Look, I'm in a class, eh? See, I call you back. But I'm coming. Poor son. Yes, I'm coming. Class, eh? Sorry about that. Anyway, this is about you guys. Anyway, fine. So, let's see how much of this we have. Sorry for a short commercial break. Okay, so yeah, now we're saying part C. So A is invertible, means A is equivalent to IN. If you reduced, there are situations where you try to reduce A using the raw operations to get this kind of thing. It's not possible. It will mean that A is not invertible. All right. I think the previous example illustrates that. So you check it, okay? You have the book, you have the notes. Then next is that the equation X equals 0 has only the trivial solution. That means our matrix which is invertible, just translate that X, the solution X equals, you multiply both sides by A inverse, which exists. So you'll get A inverse, okay, times 0. And of course, this means that X will be 0. That's what we're calling the trivial solution. Then the linear transformation, TA is 1-to-1. The linear transformation is onto. Now, let me just say something about this one-to-oneness and onto-ness. Now, let me talk from the perspective of functions. When we talk about a function, let's say f, we say f is 1-to-1 if, you are mapping, f applied to x equals, suppose you said f equals f of y. If you set this, then it turns out that this implies that x equals y. Now, this is for functions, what we're saying. And remember, linear transformation is just a function. So I just changed my f to t. So t of xy equals t of y. That means that x equals y, then t is 1-to-1. So, and then, okay, let me just translate this again a little bit here. Allow me to, likewise onto. So let me just go up again to illustrate this. Allow me to do that because this is an important factor of what I wanted to illustrate and the kind of result or question I would ask you. So you see, T is a linear transformation from Rn to Rn. So we'll say that this map is 1-to-1 if the image here, you have T of x, T sends x and y. Well, let's write it down because we are explaining what is in the notes. So T sends maybe x, suppose x comma y. These are two vectors in here. When T works on them, you have T of x, whatever that is, and suppose this is equal to T of y. So if you lift T and you have x equals y, then T is a 1-to-1, okay? Then T will be onto if T covers the whole of this. That means T is onto. So this is the criteria for, so this implies x equals y. And then T applied to the whole of Rn. Anything you pick that you are mapping, applying T, it turns out to give you Rn. Why Rn? Because of the map we have in here. If T applied to the whole of this gives you Rn, then T is onto. Okay? Now let me show you an example of this kind of two situations by even just looking at them. So if I give you, now I'm giving you examples just off the cuff. So T, I pick T, I send it to R, let's say 3 to R3. And then I have to say what T does. So my function, so I just say T is defined by, T picks three things, X, Y, and Z. These three things, I can say, what does it do? Well, I can say this equals, I can say x minus y. The first one. The second one, I put comma, y minus z. And the third one, I'll make it easy for you. I'll just say it fixes z. Okay? So my t, my linear transformation here, this, by the way, is a linear transformation. So t takes something in R3. Something in R3 would mean x, y, z. And then it gives you an output of three things. 1, 2, 3. So they go to R3. But how does it pick them? It takes x, subtracts y for the first guy, then takes y, subtracts z for the second guy, and then fixes z. So question is this well, two things I want us we want to ask ourselves based on our theorem here. What are those two things we want to ask ourselves? Is this thing well, so I want to look at the theorem, what the theorem says based on our example. The good thing is we travel with our question example here. So let's travel with it. Yay, nice, very nice. So here it is. One of the things I will do is to clear this space here. Actually, I like this system of learning. I think we should always learn things like this. Hopefully, it's making sense to you. For me, just, I don't know, convenience, at least on the board. So here we have a theorem that says that all these things are equivalent. Equivalence means that if A is invertible, then all these are true. I mean that A is invertible, that means the transpose of A is invertible. Remember, we were able to do that, previous theorem. Then there is rho equivalent to this, and so on like that, okay? And now here the issue of the linear transformation, T is 1 to 1, and T is on to. Now, I can just say, I can go by the definition of what a linear transformation that is 1 to 1 does, okay? I can say, suppose, I don't know, T of x1, y1, z1 equals this, and then T of x2, y2 equals that. Then I pull out and see whether they're equivalent. That will work, or like I just say, what do we have? Well, here now we do have a linear transformation. So the first thing is to pull out the matrix that represents this linear transformation. And do you know what the matrix of this linear transformation is? Just pick the coefficients of this. This will form row 1, row 2, row 3. So my matrix A, well, our matrix A is, so row 1 is going to be 1, because it corresponds to coefficient of x, and then minus 1, and then 0, because there's no z. So that forms row 1. Then row 2 will be 0, because there's no x for the second guy. And then 1 for the y, and minus 1 for the z. And the last one is 0, 0, 0, and 1. So ladies and gentlemen, this is the matrix of the linear transformation we have. So basically how this one works is I can say I'd have so I'm just multiplying this by x, y, z. If you put x, y, z here, I'll have this multiplied by x, y, z, I'll have x minus y. And then here I'll have y minus z, and then this will give me z on it. So this is the matrix that we're talking about. So the first question is this matrix invertible? Well, it's not too complicated. You can check whether it's invertible. Now, the criteria I didn't give you, which I can give you now, is that if the determinant of this matrix is non-zero, then we're actually okay to go. And actually, you can see what's the determinant. Well, now you guys are experts. What's the determinant of this matrix? You just use this column. So the determinant of this matrix is just 1, this 1, times the cofactor of the matrix you get. Cofactor of the matrix of 1, that turns out to be this one here. So it's just the determinant of this matrix is, I can write here for you. I don't know what you want me to do. So we are doing revision and contraction and expansion. So determinant of A turns out to be, using column 1, is just 1 times cof 1. Cofactor of 1. Right? So what is the cofactor of 1? The sign, this is just 1 minus 1 raised to 2. Then you delete this, delete that, you just get the determinant of this matrix. This is 1. So it turns out that the determinant of this matrix, by the way, is 1. And then something I can ask you, now, if the matrix was the identity matrix, what would be its determinant? I mean, the identity matrix is 1. Now I've written a very generous one. Anyway, forgive it. 0, 1, 0. Then we have 0, 0, 1. This is our identity matrix 3 by 3. Eh? What's the determinant of this matrix? It's also 1. The determinant of the identity is always 1, by the way. The determinant of this matrix is 1. So not all matrices that have determinant 1 are the identity, for your information. But the identity always is determinant 1. Anyway, so this matrix here is invertible, by the way. I've not found but it's not too difficult to find the inverse of this matrix. But you can find the inverse. And so now I can actually claim for free that this linear transformation is 1-to-1 and it is onto. This maps, because this matrix is invertible, so all you have to do is find the inverse of A. Now, can you find the inverse of A? Again, it's not too complicated. A inverse, I'm not going to find it for you, but you can find it yourself. You can use the cofactors. There's a relationship which I don't know whether I gave you, but probably somewhere in these notes, that says what? That what the relationship that says is that A inverse, this equals the reciprocal of the determinant 1 over determinant of A. It's in these notes for sure somewhere. Determinant. I'm right. I'm becoming terrible at this. Well, no. 1 over determinant of A times the transpose of the cofactor matrix of A. So it means you need to find all the cofactors of this matrix. There are 9 of them. And then you write them as a matrix. So you'll have AC. You take the transpose of that matrix, and then you multiply by the reciprocal of the determinant. That will give you the inverse. And that's not a hard job for you to do. So please do all that. Those are exercises you can do. Once you have that, then now you know what you have. You have A inverse. And once you have A inverse, then you have the inverse of. You have our linear transformation, this one. So suppose I give you this linear transformation. Then I ask you to show that the linear transformation is 1-to-1 and onto. All you have to do is pick the matrix of the transformation, which is A, find its inverse, and if it's invertible, if inverse exists, it means it's invertible. And once it's invertible, then the answer answers the question that is 1-to-1 and it's onto. And then how do you get the T inverse? And then find T inverse. What returns, I mean, the inverse of this transformation. So you just need to find that, and that's not too complicated. In fact, let me see whether we can do that here. Now, this lecture was not supposed to be so long, but it's not very long anyway. So what I'm trying to do is see whether I can steal time to show this kind of thing. So what we have here is our matrix, which is, let me write it here somewhere, maybe it will work. 1, 0, 0. Then we have -1. Then we have 1. Then we have 0. Then we have 0. Then we have -1. And then we have 1. This is our matrix A. Now I want to do the thing we have been doing here of having this matrix and then we write its augmented form. So we have 1. Ooh, let's erase this one because I'm trying to be nice. So we have, all right. Anyway, it doesn't matter. Even if it becomes long lecture, no problem. People will understand. So 1, 0, 0. And then this is 0. This is 1. This is 0. And then this is 0. This is 0. And this is 1. So you know what we are doing here? We want to reduce this to row echelon form or reduce row echelon form to get the inverse. And then we answer all those questions for our theorem. So I can just go down here and say, so what row operation will I do? I can fix the third one, is already done for us. So we can do the second one. We can just say this row is the row itself plus the third one. So we'll have, let me move. Which way do I move? Let me move this way for the sake of space. So I have my 3 by 3 matrix. The third row remains as it is because it's already done. Right? So we're good to go. This is 0, 0, 1. Now this one, row 2 becomes row 2 plus row 3. 0 plus 0, 0. 1 plus 0, 1. Minus 1 plus 1, 0. You see, this is looking nice. And then this is 0. The next one is 1. The next one is 1. I hope I'm right. So 0, 1, 1. Then the first one, we can do it very fast. What will it be? Now this one we have obtained, we can just add it to the first one. So this row plus this row, what does it give us? 1 plus 0, 1. Minus 1 plus 1, 0. 0 plus 0, 0. Then 1 plus 0, 1. 0 plus 1, 1. And 0 plus 1, 1. Guess what, ladies and gentlemen? Let me scroll down so that you can see that we do have our... We've actually finished. Now I gave you a simple matrix. Why do I say simple? Because we are now home. You see, we say with A, the identity, then we have the identity inverse. So this is the inverse of the matrix. So our A inverse, so A inverse turns out to be what? And we can check that, but it's not too complicated. Don't worry about the noise. So A inverse is, we just read it. It's actually 1, 0, 0. I just use matrix. 1, 1, 0. 1, 1, 1. That is the inverse of A. So you know what we've done, ladies and gentlemen? Again, I can tell you, we've actually inverted. We've done several things of this lecture anyway. So we've, this result, so the following statement is equivalent. So if we have our matrix A and we can find this inverse, then we are good. Because now one, I start with this question I've started in a strange way. I start with this linear transformation. And so the next thing is I pull out the matrix of the transformation, which is this one, A. And then I find the inverse of A. If the inverse of A exists, then all these other things are true. A transpose is invertible. The columns of A span Rn. The linear transformation is actually bijective. It's one-to-one and onto. And so now let's write down, because one-to-one and onto is bijective, the inverse of this linear transformation exists. Can we write it down? Oh, yes, we can. How will we do that? Well, we have our matrix, we have the inverse, so we just write it down. We just multiply this inverse matrix by x, y, z. So here I can just say very quickly. I always say very quickly. Now what have I done? So T inverse, I will now take R3. Remember, we were mapping R3 to R3. I just write it down. I can tell you for free, all you'll do is you pick this matrix and you multiply by x, y, z. I write x, y, z, and then I write down that in horizontal form. So this guy, you multiply by this, I'll have 1 times x. So it's x plus y plus z. So it will be T inverse or T of A inverse, which I'm writing as T inverse. This takes an element x, y, comma, z from R3 to, well, here I'm just writing down. This 1, 1, 1, it becomes x, plus y plus z, comma, next. 0, 1, 1 means that 0 times x is 0x plus y plus z. So it's just y plus z. And lastly, comma, 0, 1, 1. So it just takes it to z. So basically, this linear transformation, now I don't know whether I can change the color. Let me see. Yeah, we could change the color. So I can just say now, this linear transformation we start with, okay? This is a linear transformation or linear map. It's invertible. Actually, is 1 to 1 and on to because A inverse is invertible. So we find A inverse, and this is A inverse. And once we find A inverse, we actually have determined the inverse of the linear transformation. So this is now the inverse of this linear transformation. So I will finish the lecture, I hope, let me see, by just saying what we can do about this. Anyway, this was mostly about linear transformations in a very quick lecture, which is very nice. So I wanted to say, like, what we have done here is, suppose I start with t. I mean, I just apply t to maybe 1, 2, 3. So what does t do to 1, 2, 3 from R3? Well, it just does, it will give me x minus y. So it's 1 minus 2 is minus 1, comma. It gives me y minus z. So 2 minus 3 is minus 1. And lastly, it gives me z, which is 3. So that's what t does to 1, 2, 3. But now t inverse means I go back to where I came from. So let's see whether t inverse does the same. So what does t inverse do? Well, t inverse will take minus 1, minus 1, and 3. Now my hands are getting tired of this, but we are finishing. What does this do to now? T from here sends 1, 2, 3 to minus 1, minus 1, 3. All right. Then now T inverse takes me back. So if I take now T inverse applied to minus 1, minus 1, 3, let's see whether we get 1, 2, 3. So it takes the 3, you add them. So you have minus 1 plus 3 is 3 minus 1, which is 1. That's so far so good. Then it takes y plus z, which is 3 plus minus 1 is 2. And then it gives me z, which is 3. So you see, we are right, ladies and gentlemen. So what we have said is a very powerful result here. And I think now with that, I can more or less close this lecture. So basically, when you start with a linear transformation, that linear transformation has a matrix that represents it. If that matrix is invertible, then T is 1 to 1 and on to, meaning what? That is bijective, that the inverse exists. And how do you get the inverse? We get the inverse of A, and then we apply this to this variable, and then we get the inverse linear transformation. Example, this is what happens. All right. Now, I said I was going to finish, but let me just finish with one last, let me say one more thing before I finish. I mean, in this case, it's just an example for one that is onto, but is not, that kind of thing. So a linear transformation like now, if I had T sending something like, I don't know, R2 or R3 to R2, already with that, you can say something. This linear map cannot be cannot be invertible. Why can't it be invertible? Because there's no way you can pick something from R2 and get R3. Anyway, defined by T, we'll take three things. I can take X, Y, and Z, and I send these guys to, I can just pick the sums, okay? I can just say X plus Y, and I can just say, for the sake of brevity of my lecture, I just say Z. Okay, no, maybe that's not good. Y plus Z. All right. So you have given now another linear transformation. that picks elements from R3 and sends them to R2. How is that? This is what it does. Okay. So the question now for you would be, is this linear transformation, well, does this thing three operate or okay? Here now, one thing I wanted to see or to highlight is A invertible is equivalent to IN. In this case, A is 3 by 3. In our case, it's not going to be the same, okay, because you have R3. So what happens is that the linear map for this, the matrix for this one, let me just erase this for the sake of showing this. The matrix for this guy, what is the matrix for this guy? I'm deleting this. The matrix now, it turns out to be our matrix A is a 2 by 2 matrix, remember? Now, in this case, we are in trouble. Our 2 by 2 matrix, which is 1, 1. Well, actually, it's supposed to be yeah, actually, it's a 2 by 2 matrix. It should be 2 by 3 because our variables are x, y, z. X, y, z. So our matrix should be x, y. So it's 1, 1, 0, okay? And then this one, because the coefficient for z, there's no z. I mean, we don't throw away z, so it has to be x, 1, 1, z is 0, then y, z. So this is 0. And this is 1, 1. So this is now the matrix of this linear transformation. So now you can see all these theorems fail. Let me just erase it so I can show you. These things fail. Look at why they fail. So here now, what were we saying? What were we said previously? What we have said is that so A is invertible. Well, this A is not invertible. It's a 2 by 2 matrix, so there's no, you cannot talk about invertibility of this matrix. So obviously all these other things fail. Actually, everything fails. A is not invertible, then A is not equivalent to IN. Obviously, it's not. The equation will not have a trivial solution. It will have more than one solution. This linear transformation, is it one-to-one? Now you need to check that. Is the linear transformation onto? Okay. So one of these is true. Which one? I want you to check. That's your homework, okay? Number 3, this equation is always solvable. That's true. The columns of A do not span Rn. Rn is R3. R3, but in our case, this is not true. These columns span R2. So the theorem fails, okay? Now, ladies and gentlemen, I think my lecture has gone on too much, but as far as linear transformation is concerned, we are done. Determinants, we looked at this determinant business. I think we finished. So let me see what is the other thing I was going to tell you about this. Let me just scroll to see. We looked at this. We looked at this. So really, so this is a property that you need to keep in mind. I mean, the properties of determinant, okay, I actually have remembered something to finish up because I wanted to be done with the first 2 chapters, so I can go to chapter 3 in the next lecture. The properties I wanted you to remember of determinant, suppose A is an n by n matrix and B is a matrix obtained by multiplying a row of A by beta, 1 row. Then the determinant of B is beta times the determinant of A. I mean, you can check that. Then a generalization is that, so these are also the same things we are looking at. I wanted to the general form. You can look at this. I wanted to give you one which has an example. Yeah, like this one says, suppose A is a 4 by 4 matrix and suppose the determinant of A is 11. If B is obtained by interchanging 2 rows, 2 and 4, what is the determinant of B? The determinant should be the negative determinant of that one. This is what we looked at last time, so I'm not going to look at them so much. And so forth and so on. Let me see. Yeah, more properties of determinant. This one, yeah. Okay, the last thing to say before I close. So let A be an n by n matrix, and let B be matrix A scaled by beta. All right, that B is A multiplied by some scalar beta. So the determinant of B will be the determinant of A times B power the number of rows or columns of, that beta power n. The reason for that is that each of the rows of A or columns are multiplied by beta. So that's why it's beta power n. So, and then there's a proof there, which anyway, fine, you can look at that. I'll just last example for the day. Suppose A is a 4 by 4 matrix, and suppose the determinant of A is 11. What is the determinant of 3A? Each of the rows of A, there are 4 rows. They have been scaled 4 times. So basically, the determinant will be the determinant of A, which is 11, times 3, 4 copies of 3. And that's what you get. Okay. Then other things you can look at here, determinant of A times B is the same as determinant of A times determinant of B. Determinant of A power K is the same as determinant of A raised to power K, and so forth and so on. And then this is the theorem I've told you about, which you can prove also. So if A is invertible, then the determinant of A inverse equals 1 over determinant of A. This again is not too difficult to prove because all you will do is, we know that A inverse times A is IL. So we have determinant of A times A inverse equals 1 because determinant of the identity is 1. So that means determinant of A times A inverse, which is the determinant of A times determinant of A inverse. So determinant of A times determinant of A inverse equals 1. So determinant of A inverse is 1 over determinant of A. That's it. Cofactor method, I think that's it. I think the next time I'll look at something else, okay? Otherwise, I want to stop the lecture there. So let me close all this, stop recording.